Okay, hello everybody. Glad to see you here with me on the session about Kotlin, Java, code coverage, and about their best friend bytecode. I hope I will manage to present you today some scandals, a little bit of intrigues, and some investigations. And my name is Evgeny Mandrikov. I work at such a great company as SonarSource, but everything what I'm gonna present you today is just my opinion, and it was done in my spare time. And my company can only dream that they own this opinion. This is not the case. And all of this is, as I already said, done in spare time. In my spare time, I work on such project as JACOCO, Java Code Coverage. Maybe you heard about it, maybe you're using it. So let's maybe check who is using this tool, who heard about it. Okay, a lot of people. But we're not going to talk about tool itself. We're going to talk about Java and Kotlin, about something that was discovered while developing this tool, not at all about how to use this tool. And before we start, I have to tell you that it's quite hard to develop such a tool. So we have a lot of tests, and in particular we test 14.5 GDK versions, starting from GDK 5 back in the old days and up to the nowadays GDK 18. The list is long, so GDK 18 is even at the bottom of the list. It's not shown here. Why half? Because we also test early access builds of GDKs before they reach general availability, so while they're in development. And we find interesting stuff, so sometimes we find bugs in GDK. I actually should admit that most of the time we find bugs not in our tool, we find bugs in GDK. Funny fact. Well, sometimes we fix them, sometimes we propose some changes even to the GDK itself. Well, and of course sometimes we implement the new features. So for example, code coverage report for some Kotlin classes a long time ago for using JACOCO version 0.8.1 was looking like this. So you could see that there is a lot of red lines, and there is not so big percentage. There is zeros, there is not everywhere 100. And we implemented some new features, and the report, without any changes in the user code, in the tests of the user code, started to look like this. Now it shows 100% everywhere, everything is covered. Why this happens and what exactly the new features we implemented, that's exactly what we're gonna see today. Before we start, it's important to understand that JACOCO receives all the information from the class files, not from your source files. It reads the result of compilation of your source files into the class files and performs analysis of those. This is an interesting thing to do because it actually allows us to simplify process of integration of JACOCO into your application, into your tests, because in fact it's as simple as launching Java virtual machine with a Java agent. It's just one more option to add to the startup of Java virtual machine. It also allows us actually to compute code coverage without any access to the source files. So you can actually take a jar. If you don't have a source files from which this jar was made up, you can still compute code coverage. It's not a problem. And the fact that we analyze not the source code but the bytecode actually simplifies our life. It allows us to easily cover new syntactic sugar that appears in Java language. So for example, text blocks, which were introduced as preview in GDK 13, it's not a big deal for us at all. It was zero changes on our side, it's just a syntactic sugar. It produces exactly the same bytecode as before, so nothing to do here. And there is other examples of such syntactic sugar. Maybe in future we will have concise method bodies, and we believe that it wouldn't be a big deal for us to deal with them. But not all of the language features are actually syntactic sugar. So for example, lambdas are not at all a syntactic sugar. So for lambdas, we actually had to do some job. But let's move forward. And the fact that we analyze class files actually opens a door for us into the world of other JVM-based languages, such as, for example, Scala, Groovy, and Kotlin. And today we are going to talk about two of them, about Kotlin and Java. And here is my usual real disclaimer before we really start. Sorry for you. Today there will be a little bit of blood out of JVM. If you're not ready, the door is still open. Sorry, we are going to see naked Kotlin compiler and naked Java compiler. We are not going to use IDE. We're not going to use anything else than just a command line to compile our source files into the bytecode. And we're going to talk a strong language with you today. We're going to talk bytecode mainly. But I will try to simplify for your understanding of this maybe new language. And within half of an hour, I will try to do a little bit of intense violence of your brain. Sorry for this. If you're not ready, again, door is open. So, are you ready? Let's go. Let's start with Java. Let's start with Java language specification. With Java virtual machine specification. Java virtual machine specification in paragraph 4.7.8 has a pretty interesting statement. I'm not going to read it all, but basically, everything what was not presented in the source code, but presented in your class files, should be marked in the class files using a special synthetic attribute. And there is some exceptions, as in every language to every rule in the Java language, there is exceptions. And there is some exceptions. For example, this doesn't apply on the compiler-generated methods, such as methods of enums, default class initializer method, default constructor, and methods of records, which are generated. So, let me ask you a question. Why there is a need to generate something in your class files which is not presented in the source code? And why there is a need to make an exceptions to this rule? Do you have any idea? Well, actually, no, but okay. You just have to be careful. Everything today, I'm not doing a tricks with you. Everything today, what we're gonna see, is shown on the slides. You just need to be careful. The last paragraph, which I didn't read, answers this question. The synthetic attribute was introduced back in JDK 1.1 to support nested classes and interfaces. That's why. What's so special with nested classes and interfaces? Let's see on practice. Let's take a simple program, example.java. We have an inner class, we have an outer class. Inner class has a private constructor. And in the outer class, we have invocation of the constructor from some method. So, first of all, is it valid Java code? Seems so. Let's don't guess. Let's try to compile it, and that's basically what we're going to be doing today. We're going to take an example. We're going to use javac Java compiler to compile this example, and we're going to use another tool which is part of JDK, JavaP, so-called Java Disassembler, or you can call it decompiler, whereas actually it doesn't produce back you nor the assembler nor the Java, nor the result of the decompilation. It actually just shows you the bytecode in a human-readable form inside of your class files. So today we're going to use just actually 3 tools: compiler, 2 compilers, and 1 JavaP. And my favorite options for this command JavaP, it's -v and -p. -v, be verbose as possible. -p, show everything, show privates, etc. Show everything what is hidden in class files. So, if we will use this command on the class files that was produced for the outer class, we're going to see the following. I use it at Java compiler version 8, so we see that major version of class file is 52. It corresponds to Java 8. We could see our method where we had a constructor invocation. here is actually the constructor invocation. But what is strange with this constructor invocation is that it takes some null argument. Our constructor, as you might remember, was not using any argument at all. Why so? In order to answer on this question, we have to look on the result of compilation of an inner class. So the same java p minus v minus p, name of the inner class. And in the inner class, we could see here is, okay, our private constructor. Here is our constructor with a parameter. What's interesting about this constructor is, yes, it is syntactic. And unlike our original constructor, it's not more private. It's now package local. And yes, it takes some parameter. So why it is package local now and why it takes some parameter? It's package local now because while from the Java language perspective, what we just wrote in our source code is perfectly valid, in the Java virtual machine, it's not at all valid because those two classes, they're not nested in each other inside of Java virtual machine. They lie next to each other. And one class cannot have direct access to the private members of the other class. So Java compiler developers have to introduce this quirk, this trick, in order to overcome this discrepancy between Java language specification and Java virtual machine specification. They have to generate package local constructor that can be called, which is no more private. And in order to not clash with the original constructor, they have to make a distinction between in signatures of one and another. And the difference makes by argument. And yes, this constructor simply calls the private constructor. And the argument, which is actually null, is another generated class, which is also syntactic. This class is actually empty. It doesn't contain anything. You cannot even create an instance of it. This is just a marker for this constructor. So it's also synthetic. All this was back in times of Java 8. But as you might know, Java nowadays evolves quite faster. We already have Java 18, Java 19 is around the corner. And thankfully, in Java 11, all these discrepancies between Java language specification and Java virtual machine specification about access to the private members of nested or outer classes, this was solved. There was a JEP 108.1, call it nest-based access control. So let's have a look what changed with Java 11. If we're gonna compile exactly the same source code with Java 11, we're gonna see following. We're gonna see major version 55, which corresponds to Java 11. And we're going to see that there was a significant loss in weight because there is no more the need to generate this package local constructor because the notion of nesting was actually added to the class files so that virtual machine can now verify and know which class is nested to which. So there was a new attribute, nest host. Let's have a look on another example. It's also simple. We have, again, outer class, we have a private field in outer class, and we have an inner class. Inside of an inner class, we have a method which does an increment of a field in the outer class. Again, question the same. Is it valid Java code? Can we do so? Yes, it is. Probably, why not? Let's again check. Let's compile. If it compiles, then it's valid code. Yes, it compiles. You probably already can guess what we are going to see inside of the bytecode. There should be the same trick, right? We are making access to the private field from the inner class, so there should be something similar. Let's have a look. So it's again Java 8. Here is where we do increment. And indeed, instead of increment, we are going to see invocation of a strange method inside in the outer class. What is this method doing? Again, it is package local synthetic. It provides access to the field, which is private, and it actually contains the increment. It's the same trick as they was doing for the previous example. It's just slightly different because we are performing access not to the method, but to the field. And again, the same thing in Java 11, this was improved. There is no more need to provide such a method. there is a new attribute. Now we see nest members. Nest host was saying into whom we are nested. Nest members saying who are nested into our class. So these two attributes, they define the relation between two classes. And there is no more need to introduce such synthetic methods to provide access. At this moment in time, you might start wondering, so no more need to have a synthetic attribute? We covered the initial need for which it was introduced, right? Seems so. Actually, no. There is another example where synthetic attribute plays a role. We have two classes, class A and class B. Class B extends class A. They both have a method. One class overrides a method from the base class. The only difference is they have different return types. Again, is it valid Java code? Probably it is. Let's compile and see. If it compiles, yes, it compiles, so it was valid Java code. So what we're going to see again, Java 18. Here is a method fun in the class B, which extends class A. It indeed has a signature. It returns string. And here is another method in the same class. It has almost the same signature, but now it returns object, and now it is synthetic. Why so? Because due to inheritance, every place that accepts interface of A should accept also the parent of A. So in every place where we can pass instance of class A, we should be able to pass instance of class B. But every place that uses interface of A believes that A contains a method which returns object. But instances of class B contain a method which returns string. So to bridge this gap, what compiler introduces is so-called a bridge. And it is synthetic. It is not presented in the source code, but has to be presented in the bytecode. And it simply delegates to the original method. So, enough quirks in Java. Let's talk about Kotlin. In Kotlin, by the way, how many of you use Kotlin? Oh, a lot of people. Okay, then you probably know. In Kotlin, we have data classes, right? So we have such a simple data class. It contains a single field, x, and that's it. It is empty. Who agrees that this data class, beside the field x, is empty? There is nothing. There is no methods in it, right? Okay, so now there is a right answer. There should be toString, probably equals, etc. Where they are? Let's try to see. Let's compile. Let's compile using Kotlin compiler. Let's decompile using again Java P. And we're going to see indeed it contains field, and beside field it contains method getX, getter for the field, but it is not synthetic. It was not presented in our source code. We didn't write this getter. It is in the bytecode, but very synthetic attribute. Why it was used in all other places where a compiler generates methods, but not there? One might say, oh, that's Kotlin. Kotlin is not Java. Kotlin doesn't need to follow the Java rules, right? You seems to be disagree. So probably it's a wrong answer. Okay, the correct answer is there is no way for the user, for us, for the developers, to write the source code which will be calling a synthetic member, except using reflection. So there is no way in the source code to really write an invocation of a synthetic member. Access to synthetic members is only allowed to the compilers. However, such methods as equals to string, methods of enums, values and value of, and etc., even those that are generated by compiler, user also should be able to call them, to write in the source code here is my data class dot get x. And that's why they cannot be marked as synthetic. That's why there was exceptions to this rule in the Java virtual machine specification. All the methods that user should be able to call, but should be able to call and are generated, they do not have a synthetic attribute. So here is method setX, the same story. Here is constructor. We didn't write it, it was generated, but it's not synthetic. Here is a beautiful toString, which was generated for us. Here is a hash code, equals, and so on. Why all of this comes out of the work on Jacoco? And why there was such a difference between two reports of generated by different Jacoco versions? Because if something is generated by the compiler, it's strange to test it. Probably we just should trust the compiler that the generation of this thing is correct, and we shouldn't require testing of this. So Jacoco shouldn't be showing you those methods. He shouldn't be yelling on you and saying, "Oh, please test equals. You didn't test it equals here. Why do you need to test equals if it was correctly generated by the compilers?" So for us, developers of Jacoco, we have to solve the task how to distinguish such a method which has no synthetic attribute, which probably was generated by a compiler, how to distinguish it from the method that was actually written by the user. Maybe you wrote your equals, and we have the generated one, how to distinguish one from the other. And that's what we do in Jacoco. Depending on the case, we solve this case by case. In this particular case, a nice trick is every method generated by Kotlin compiler doesn't have a line number table. It doesn't contain line numbers that correspond to the source code. Every generated method is not gonna have the source line numbers. That's how we can distinguish for Kotlin classes which methods are generated, which are not, even though they are not marked by synthetic attribute. So that's how the report was looking. It was showing those methods, those members. We wrote a filter that says, oh, there is no line number, then filter out the method. And that's how the report started to look. But let's move on. Java evolves. So if several years ago there was no equivalent of the data classes in Kotlin, nowadays there is, as you might know. In Java 14, records first appeared as a preview feature. They're quite similar to the data classes, right? Let's have a look what is inside of the records. And you probably might guess that we're going to see pretty much the same thing. We're going to see the field, we're going to see the generated constructor for us, we're going to see the toString method, hash code, equals, getter, and so on. What is funny is, unlike a Kotlin compiler, Java compiler, if we ask it, the Java compiler, to generate line numbers, Java compiler would generate line numbers even in the methods which are not presented in the source code. The Java compiler here says to us, the method toString actually corresponds to the line number 1 in your source code. So such generated methods, they always correspond to the very first line of your class. So our filter which we implemented for Kotlin doesn't work anymore, and we have to imagine something else. Thankfully, methods generated for records, they contain a special structure, they contain a special instruction invoke dynamic, and there is no... And it's easy to distinguish those methods, basically. If it's toString, which contains a special invoke dynamic, we know that it's a method generated in the record. So let's move on. Let's get back to the Kotlin. As you might know, Kotlin also has when expressions. So for example, we have a such code. We have one enum. It has two values. And we are using this enum in another method. We are simply doing when expression, or let's say switch by the enum values. So there is two cases in our switch, right? We compile this. What we are going to see in the bytecode? We are going to see indeed a switch, but strangely enough, it contains now 3 cases. We wrote just 2. Why there is a third one? And what does it contain? Let's have a look. So here is the first case, here is the second case, and here is a third case. And third case is simply, hey, throw an exception, no when branch matched exception. Why do we need this third case and an end exception? Sorry? For the exhaustivity of the switch, but why we need exhaustivity of the switch? Why we need switch to be exhaustive? Split compilation. If the class where we have a switch and the enum is actually not located in the same source file or not even in the same project, then it is possible that enum is modified independently from the switch, and they are compiled by different parties. So it's possible that the switch was compiled, then enum was modified and recompiled again, so that now there is more values in enum than this switch was originally expecting. So we cannot just fall through this method into the void. We have to handle this case. And the best way to handle this case is to say, well, this switch was not designed for the new value of the enum, so let's throw an exception. What we also could see in this example, we could actually see that the switch is not done by an ordinal value of the enum. The switch is actually done by some strange value taken from an array which resides in a class whose name contains words when mappings. What's that? Let's have a look into this generated class. It's synthetic. It contains only static initializer. Inside of this static initializer, we see the following construction. Mappings is a new array which will have exactly the same number of values as enum. And such assignments. Let's take ordinal of a constant false, and let's assign and into the position in this array that corresponds to an ordinal of constant false, let's assign 1. For the position in this array that corresponds to an ordinal value of constant true, let's assign 2. And we're going to use these values in the switch. Why such trick is needed? Why do we need to map runtime values of enum constants to some constants, 1 and 2? Exactly. The same thing as before, split compilation, because not just the new constants can be added to the enum, but also the existing constants can be reordered. If we would just use the original ordinals of the enum during the compilation of when expression, then after the change of the order, our switch or our when would behave differently than at the compilation time. So we have to do the mapping. We have to assign the current runtime values of ordinals to some known constants that was there at the compile time. That's the trick. Of course, Java has the same construction since forever. There is no magic, there is nothing new. But let's try to see if it's at all different on the bytecode level. What we can see, here is a switch, here is the enum. We see here is method, here is a switch. Indeed, this switch also uses array. It also performs the same access, but this time the name of the class is slightly different because it's a different compiler. What we could see, this class is again synthetic. It again contains a field that provides mapping. It again contains static initializer, and it looks like everything is the same. We're again assigning 1 to the ordinal value of false. We assign 2 to the ordinal value of the true. But can you spot the difference? Actually, there is something different to the previous example. They're the same, but not quite. Yeah, I almost spoiled an answer. It's exception table. The previous example didn't contain such an attribute as exception table. Exception table in the bytecode, it simply says from instruction number, in this case 9, to the instruction number 20, if exceptions no such field error happens of a given type, then jump to the handler of this exception, which is at bytecode instruction number 23. And there is two such, let's say, try-catch blocks in the bytecode for such a static initializer. What they're basically doing, they're wrapping these assignments into try-catch no such field error. And they're simply ignoring this error in case of Java compiler. So in case of Java compiler, if we remove value from the enum, the switch still will be working. As like if the value never existed, we couldn't just reach this branch anymore because there is no more such value in the enum. What will happen with Kotlin? There is no such try-catch, so you would actually see no such field error when running the code compiled against the old version of the enum where the constant existed. Funny slight difference between two languages. Even though they're pretty similar, there is some difference. Okay, time to rest a little bit, time to breathe. Here is a quiz for you. Now we know how when expressions on enums are compiled into the bytecode, so I hope it will be easy for you to answer what is going to happen after execution of a such program. There is two enums. One enum, x, contains two methods. Initialization method, init, and a method whose interesting name is neverCall. Both those methods, they have a when expression, and they just do a switch on two different enum instances. The init method uses enum y, and neverCall method uses enum x. And what we do in the main entry point, we just want to print enum constant a from enumeration x. Okay, I can give you some options. Option number one, this doesn't compile. Who agree? Okay, nobody. Option number two, it just prints a. We ask it to print enum constant a. It uses toString on enum. toString on enum is the name of enum constant. It's going to print a. Who agree? Okay, there is one person. Okay, maybe it does something else? Who agrees that this does something else? 4 more persons. So we have 5 in total, and I don't know, about 20 people in the room. Sorry, but I ran out of options. They, as we said earlier, they're pretty exhaustive as our switches. Okay, let's don't waste time. Actually, it's going to throw a null pointer exception. No, in fact, it's going to throw exception in initializer error, which is going to be wrapping a root cause, which is a null pointer exception. And some time ago, somebody told me that null pointer exception in Kotlin is so rare that it almost never happens, especially when your program doesn't contain null values and nullable types. And well, this program does not contain nullable types, and this program doesn't contain the null values. But it throws a null pointer exception. This is a compilation quirk. This is a clearly compilation quirk and the problem in the compiler. It's probably so rare problem that it's not worth fixing because it's a well-known since since a long time, but the cost to solve it is higher than the need to solve it. And actually, exactly the same problem exists in Java. You can construct exactly the same example in Java, and this will be maybe a home exercise for you to try. What's going on here? What happens? As you can see in the code, it points exactly at the static initializer of when mappings class that we saw earlier. Why? If you look at it this time, we would see that because we have two when expressions in our class, we have to initialize two mappings. One for one enum constant, y, and the other for another enum constant, x. And in order to initialize the mapping for enum constant x, we need to know how many enum constants there. We are going to call the method values on x. But we are doing switch in initialization method of x. So x is not yet initialized, but we need to construct those when mappings because of never call method, which contains the switch by x. So it's initialization problem. X is not initialized, but we already need it. So null pointer exception. Such a trick. Okay, let's move on. Java evolves. In Java 12, we got switch expressions finally. Probably you already can guess what we're going to see inside of the bytecode of switch expressions. If we compile this with preview features, then indeed we're going to see also three cases there. And the third case is exception, but in Java it's slightly different. It's incompatible class change error. This switch is not expecting that enum changes in a way that a new constant is added. Pretty much the same as in Kotlin. Let's move on. In Kotlin, you know, we have smart casting, and in Java we got pattern matching for instance of in Java 14. Here's how it looks in the source code. If we got an object, we can ask for instance of as always we've been doing, but we don't need to introduce explicitly any cast now. We can simply use pattern matching, declare the variable, and this variable will have the type that we are expecting. What's so interesting about this pattern matching instance of? If we compile this, and this is actually what we did once we discovered this feature in Jcoco project, we're going to see, here's following. 58 is major version of Java 14, and minor version 65,535 denotes actually enablement of the preview features. We're going to see that here is our condition, here is instance of, but bam, there is another condition. In our source code, there was only one condition, but in the bytecode, there is two. Okay, you already probably tired. It has been a long time since the beginning of the conference, so I'm not going to bother you to read the bytecode. I'm just going to show you equivalent the source code to the bytecode just shown before. This is how the instance pattern matching instance of was implemented in the Java compiler as a preview feature. In order to introduce a variable in the scope of the if, they were placing an assignment inside of an if. And in order to place an assignment inside of an if, you have to add one more comparison. This is a pretty stupid comparison because the result of this comparison is always true. But this is a way to introduce assignment inside of the if statement. And actually, this feature in the Java compiler was implemented as a syntactic sugar of already existing constructions. So it was just transforming one syntaxis to the other syntaxis, and then performing compilation of this. That's why bytecode was looking like this. Unfortunately, we discovered this thing quite late in the development cycle. It was past the release, so we reported it a bit later. We said this is unfortunate that in the bytecode we have a dead condition and the code which is useless here. We reported it, and thankfully it was fixed later on. In the next version, there is just one condition. There is no need to do such a comparison. if instead of implementing this feature as syntactic sugar, if you directly do the translation from the source code to the bytecode. Bam. Let's move on. Another interesting feature, and I guess we run out of time, so this is gonna be the last for today. Another interesting feature that was recently introduced in Java is pattern matching for switch expressions. Now in switch expressions, we can write cases in a way that it contains conditions. And so do the pattern matching. If we got a string whose length is 0, it's going to be our first case. Then if we got a string whose length is 1, it's the second case, and so on. If we compile this, if we decompile this, we're going to see following. Indeed, it's a preview feature. It's still preview feature in Java 18. Then we see the bytecode. In this bytecode, here is condition of the first case. Nothing strange here. There is just one condition. We check the length as exactly as written in the source code. Here is the body of the first case. It just prints first case, nothing special here. If there is no match on this first condition, there is also no magic here. We are just gonna go back at the beginning of the switch and ask a special method to give us next index, which we should try in this switch to do the match. So do the restart. Basically, this jump says, we already tried to match the first case. Please give me the number of the case that we should match next. And we're gonna jump to the next case. No magic here. Nothing strange here. Here is instruction that provides us with such an index. And in terms of Jackaco, there is also no problem. Switch contained 4 cases, and in the bytecode, switch also contains 4 cases, all the conditions, all in place. There is nothing hidden, there is nothing to filter out, there is nothing to fix. Seems so. This is the case till the moment when you look at the line number table. If you just look on line number table as you are doing right now, well, there is some mapping from the bytecode instructions back to the source code, and what? Nothing strange here. But if you will try to look at those line numbers while stepping through switch in the debugger, or, for example, looking on the code coverage report, you would see something strange here. And we reported this as another issue. And this time we was quite, oops, I don't have an internet. Okay, not a problem. And this time we was faster. We even reported the problem before the release and even before the switch pattern matching was actually introduced in the code base of the OpenJDK. And we've been basically saying, well, while stepping through such switch, the debugger will be misleadingly showing you strange numbers which you don't expect. And that was a nice discovery. And I wanted to show you some other quirks, but unfortunately we ran out of time, so let me skip till the end. Let me do quickly the conclusion. So the conclusion of this talk is, first of all, source code is not bytecode. What you see in your source code is not at all what is gonna be executed. What is gonna be executed is a result of a work of the compiler. Be careful, dragons are here. Different compilers may have different quirks, as we saw with null pointer exception in the Kotlin. Be careful. It's not at all what is gonna be executed, not even the bytecode. If you know, there is also just-in-time compiler which is going to take your bytecode, smash it into the native code, and execute already the native code. And dragons are here as well. The just-in-time compiler might also have bugs and might produce strange results. Be careful. Another conclusion out of this is bytecode-based tools have to guess, have to do their best to guess what you actually wrote in the source code, because they don't analyze the source code, they analyze the bytecode. And this might be quite hard. So please bear with us. So if you see something strange in Jacoco reports, don't scream, "Oh, I found a bug." No, now you know, you just go look at the bytecodes and you probably would see something interesting here. And then you can come back to us saying, "Oh, I found something funny here in the bytecode. Hey, maybe we can think how to filter it, or what are the problems with it, etc., etc." And that's it, folks. I hope you enjoyed.